In this video, we're going to discuss the physics of hot air balloons. Why on earth can we get a hot air balloon to lift? Why does it take off? This is all about buoyancy. If you have an object and it has a lower density than the surrounding material, that object will float. So it doesn't matter the size. If you have a large balloon but it has a low density, and you have air outside that comparatively has a higher density, well, they'll bump into each other. Particles will bounce in and bounce off and bounce around and hit each other from all directions. What'll happen, though, is because the thing with low density weighs less for the same volume, on average, anything inside the low density area is going to get hit up farther than the heavy objects will. Heavier components take more energy to get going faster. Gravity is always pulling everything down. As they all balance and shift around, bouncing into each other, it's just easier for the lighter weight things to go up than it is for the heavier weight things. And so as they jostle and bounce over time, they will very slowly have the lighter weight things shift up, while all the heavier weight things will shift down. This is why a helium balloon will rise. The helium inside the balloon has a lower density than the air around it. As long as there's enough helium to account for the extra weight of the balloon will rise. This is why if you have a helium balloon that's deflated over time, it eventually sinks to the floor. The balloon material adds extra weight, which means it changes the density. Buoyancy is based on when things have different density. If you are neutrally buoyant, then you have the same density. That is usually the easiest spot to start to do calculations. So let's explore for a minute. Let's find the density of a balloon. Let's just say I have a balloon. It has helium in it. It's 1 atmosphere. Our balloon here, we'll say, is 3 liters in size. And it's 273.15 Kelvin out. Well, I could have an equivalent volume of air right next to it. No balloon, though. We're just looking at the space. So this is a physical balloon wrapping around helium. This other bit is just airspace. We drew a circle to talk about it, but there's no material there. We're just talking about the air that takes up an equivalent 3 liters of space. Well, air is mostly dinitrogen. So for simplicity's sake, let's consider that it is all dinitrogen. What we can do is we can compare the densities. So let's find density of the helium balloon, and let's find density of the equivalent space of N2. What we need is mass over volume. If I can find those, I can find the density. Well, I have a pressure, I have a volume, I have a temperature. PV equals nRT. I could rearrange and solve for N. Move the RT down. We'd solve for the moles. If I know the moles of my gas, and I know which gas I have, I know the mass of it. 1.0 atmospheres, 3.0 liters. Let's assume I give us a few more sig figs there. R value, 0.08206. Atmosphere liter mole Kelvin, and 273.15 Kelvin. So standard temperature and pressure. Calculate this out. We can find the moles of our gas. We'll find there's 0.134 mole of gas. Notice we didn't target helium or nitrogen there because it doesn't matter which gas. The moles will be the same. Our ideal gas law does not care which gas it has. There is just that many of each gas inside of its space. However, helium weighs less, so if we find the mass of helium for this many moles, 0.134 mole of helium, and 1 mole of helium is about 4.00 grams of helium. So 0.5354 grams of helium. And if we wanted, we can put that into the volume. So 0.5354 grams over 3 liters. What we'll find is that the density of helium is 0.178 grams per liter. If we do the same thing for the mass of N2, well, same number of moles in the same space. But this time, 1 mole is 28.01 grams. We'll find 3.75 grams of dinitrogen. Divide that by the 3 liters, the volume that we're using, 1.25 grams per liter. For the same space, the helium just weighs significantly less. In fact, for the 3 liters that we're using, we can find the difference in weight. We can say, hey, it is 3.75 grams for the N2, and there is 0.5354 grams of the helium. Whatever that difference is the lift capacity. That difference is how much extra weight you could attach to the helium, and it would still, well, in this case it'll be neutrally buoyant, but it still won't be heavier than the air around it. And what we find is that's 3.22 grams of extra. This is the available weight for your balloon. The rubber, the dangly little streamers, anything else, this is how much extra weight the materials of the balloon could weigh, and our helium balloon would still balance out to be just as dense as the air around it. As long as your balloon, streamers and all, weigh less than that, your balloon will float. It'll take off. If it weighs more than that, then your total density for the helium balloon, helium plus materials, will be too heavy. Why do balloons float? If they do, because their density is, in total, of gas and material, less than the equivalent volume of outside gas. This is the trick to make anything float. So how does that go back to hot air balloons? Well, a hot air balloon, you have a balloon, and they're a little bit different. They have an open port on bottom. There's originally some gas inside, and there's an equivalent gas outside. Now, because it's an open port and it's a balloon, your pressure is always the same. My pressure in is always equal to my pressure out. Our pressures don't change here. Because it's a hot air balloon and it's made of fairly rigid material and has an open port, it also doesn't change its volume. Once it's inflated, puffed up at least, that open port on the bottom, gases can leave it or enter it. So you're not sealing it up like you would a rubber balloon. Our volume is constant. Well, since the outside atmosphere doesn't really change its pressure very much, what this effectively means is that pressure and volume don't change for these calculations. What's happening with a hot air balloon is you actually have your moles and your temperature that are altering. If we think about just the gas inside, well, as you make a gas hotter, it expands. The particles are bouncing faster, and so they push out. If I have a start balloon, and over here I have an end balloon, well, let's color code a few things. Let's say I have that green gas on the inside, and I still have the outside air just as before, But now what's happened is the green gas on the inside has flowed out. For all intents and purposes, originally it needed, this volume, the volume of the balloon. When you got it hotter, it needed a bigger volume. It wasn't enough to just be inside. It needed a larger volume to deal with the increase in temp. Your gas itself physically expands. The actual gas does change its volume. The balloon doesn't, but the gas does. Well, since we're only ever looking at what's in the balloon, we have to cut off that chunk of gas that left. What actually happens is that once we heat up our balloon, if our temperature goes up, the moles inside the hot air balloon go down. We've pushed some of those moles out of the balloon. They're no longer present in it. Well, if you don't have as many moles in the same volume, you don't have as much mass in the same volume. Heating a hot air balloon pushes some of the gas out of it, decreasing the mass of the air inside the balloon. As a result, its density goes down, which makes it more buoyant. This is the idea of how a hot air balloon is working. Let's do an experiment with it. Let's try and solve a little bit of this. Let's say we've got outside atmosphere, it's N2, so it's 28 grams per mole. We'll say the outside is 28 degrees Celsius and 1 atmosphere. We have a balloon. And we have stuff hooked to it, gondola. We're going for a hot air balloon ride. We've got your little device, it's making some flame, it's going to heat up that gas. Well, the balloon, you don't want to get too hot. So let's say the max heat in the balloon is 39 degrees Celsius. And a little bit more detail. So we have it we're just going to pretend the atmosphere is fully dinitrogen. And I'm going to tell you the density of the outside is 1.27 grams per liter. These are our assumptions. It's pure N2, these temperatures, this pressure, this density of the outside air. Our balloon is actually a very small one. Let's assume it's a weather balloon. There's not really a person inside it. We're going to have a balloon that weighs just 1,000 grams. So 1 kilogram of materials. What I want to know, what we're going to solve, is how big does this balloon have to be neutrally buoyant? So basically, what's the minimum size? If your balloon's too small, it can't lift anything. But if you have a bunch of balloons lifting, well, then you have a bunch of small forces all trying to pick up. Movie Up wasn't quite realistic, but the more balloons you have, the more weight you can lift. And so what size balloon will get us neutrally buoyant? So we're going to find volume needed for neutral buoyancy. Well, how do we go about doing this? To get a balloon to float, it needs to be lower density than outside. To get it to sink, it needs to be a higher density than outside. To be neutral is right when they're equal. So if I want something to be neutrally buoyant, I need their densities to be the same. Since we're comparing a sample of air that's the same size as the sample of gas, whatever size our balloon is, their volumes are identical. So the only thing that's different for their densities is going to be the masses. So, well, yes, I want my density of the outside to match the density of my balloon. The reality is, since they're the same volume, what I really want is my mass of the outside to equal the mass of my balloon. If those are equal, I will be neutrally buoyant, because whatever size my balloon is, I'll be looking at an equivalent size of air. What is my mass outside? Well, think about density. Density is equal to pressure, molecular mass over RT. But density is mass over volume. I can solve my mass for the gas. I need to multiply the volume over, but this lets me solve for the mass based on pressure properties. So I can find the mass of my outside. It's going to be my density of the outside times the volume. Well, if I think about the mass of my balloon, what makes up the mass of my balloon? Mass balloon is going to be two parts. It's going to be the mass of the gases plus the mass of the material. We know the mass of the material, that was 1,000 grams. We need mass of gas, and we just said, hey, I can solve the mass of my gas. And so I can say, well, what is the mass of my gas going to be? It's going to be the pressure, the molecular mass, the volume over RT. And then we're going to add the 1,000 grams for our materials. So we wrote it in two different ways. One side we wrote out the full ideal gas law to calculate the mass of the gases in the balloon. And one side I just left it as density times volume. Why I can do this? Well, we know the density of the outside. That's already something we knew. But we don't know what density the inside is going to be yet. And so we need all those separate components because we don't have that value. But we do know the pressure. It's 1 atmosphere. We do know the temperature our balloon's going to get to. It's 39 Celsius. And we know the molecular mass of the gas. It's dinitrogen. So we have the variables to solve that mass component of the gas inside the balloon. What we need to do then is plug in some values and rearrange. 1.27 grams per liter times volume is going to be our density of the outside times its volume. Our inside is going to be 1.0 atmosphere, 28 grams per mole, unknown volume, over 0.08206 atmospheres, liters, moles, and Kelvin. And the temperature for our balloon, 39 degrees Celsius, so 312 Kelvin. On top of that, plus 1,000 grams of material. When we think about units, atmosphere and atmospheres will cancel. Moles and moles will cancel. Kelvin and Kelvin will cancel, but grams and liters are going to be around still. Which is kind of what we wanted. We wanted grams and liters times volume, and we have grams and liters times volume. And so we indeed have density on both sides. We just had to solve it for the inside the balloon. Well, this is going to give us 1.27 grams per liter times volume equals 1.093 grams per liter times volume plus 1,000 grams. So we've taken the idea of what we needed to be neutrally buoyant was equal densities. Given that we had a set volume that we're comparing, we realized that, well, the densities are really based on the mass. We're looking at two identical volumes, so we need the masses total to be the same. What was in the masses? Well, for the outside air, it's just the density times the volume. For the inside, it's the lower density of the gas that gets hotter plus the extra weight of material. I need volume on its own, so I need to rearrange, subtract 1.093 grams per liter times volume from both sides. What we'll end up with is 1.27 grams per liter V minus 1.093 grams per liter V is equal to 1,000 grams. I can pull volume out of both of these. And what we'll find is 0.177 grams per liter times volume equals 1,000 grams. Divide by 0.177 grams per liter on both sides to get volume on its own. What we will find is that volume equals, our grams are going to cancel, 1,000 divided by 0.177 is 5,650 liters. What we found is, go way back to our starting equation here, we found the volume needed. Basically, if I had a small circle, there'd be a small mass of N2. For that same small circle, well, at higher temp, there'd be a lesser mass. So maybe I had 3 dots in there originally, and now I only have 2 dots, 1 left. And so at the higher temp, there'd be a little bit less mass in our balloon. But if the balloon weighed more than that 1 dot, I still wouldn't float. So I'd have to make a bigger one. Well, this volume will have some amount of gas in it. But at the higher temp, there's going to be some gas that's pushed out. By going to a bigger volume, what we find is that for the same temp, it will be the same percentage difference. 1/3 of the dots have been removed, but the total weight of those dots that are removed, so the moles that are removed, goes up. And we just need the total weight that's pushed out to equal 1,000 grams. So that is, how big do I need to get before I've pushed out enough that those 3 dots, or 4, however many it takes, equals 1,000 grams. The bigger my balloon gets, more total particles are no longer included at the higher temp, and so more weight is lost. How big did I need to get before 1,000 grams was lost? That's what we found. I needed to be 5,650 liters in size before 1,000 grams had been lost.